and welcome to another video where we are slowly working through a problem. Today will be a couple of problems on what we call topic, let me just change my color here, there we go, topic 12, which is on the chi-square test. Now, in the introduction we had previously, we discussed two chi-square test. So we'll have two problems that fit each of those. Here, of course, this is part B, where we work through some problems following the discussion, the introduction of the concepts that was done in the previous video. So let's go to our favorite book, Statistics for Psychology. We're going to be on page, I think, 577, and just do a basic number 13 here. Carry out a chi-square test for goodness of fit for each of the following studies, and we'll just do the first one. So they don't tell us the whole story, just to keep things nice and simple. And so we are observing some people, and we're seeing if according to these categories they are distributed the way we would expect. Okay, so we don't know what the categories are or what the people are about, just to keep things fairly simple. So first of all, we need to write down the number here. What was that number? 13. 13, and we'll do part A. Just going to make my cursor a little bigger. I need to copy this down, all the information. So we had category 1, 2, 3, 4, 5, and 6. Really the maximum I want to go to when doing it by hand, but we won't let it get too out of hand, because we're kind of limited to what we can do by hand, right? So enough to get the idea, but not too much to be overwhelming and frustrating. So here we have 6 categories, and each one has its expected frequency, giving us the distribution over these categories. These percentages might look familiar to you, but it really doesn't matter for this. Some distribution could be something familiar or not. Then we observed, oops, that was supposed to be a V, observed some scores for people we survey or whatever the story may be. We got 5, 15, 90, 120, 50, and 20. So that's where we're at, just like they give us in the question. So the first thing to do is perhaps write the start of the hypothesis testing procedure. We have our two populations. If you want to think of it in the detailed systematic way, the way we usually lay it out. Now, this is a little bit more vague because we don't know the story behind it. So our first population is, let's say, people like those in the study. We can't really be more specific because they don't tell us anything in the story. And then we're comparing that to people who follow the expected distribution according to these categories. People, let's say, just say it casually here, who follow the expected distribution. So we can't be too specific here. It's based on the information the question gives me. Our hypothesis tests, or hypotheses for the test, our null hypothesis is that the distribution of the two populations, the distributions are the same. So I'll just say it like this: distributions are the same. And of course, the research hypothesis, which we secretly want, that's how I sort of imagine it, is that the distributions are in fact different. So just because we look at the observed and see, well, if I add these up, let's add these up, see what we get, show it in the chat. So we have something to look at. I'm adding 90 and 120 and 50 and 20, and I get a nice convenient 300. If I then look at, well, 2% is expected for category 1, 2% of 300. Let's do that. So it's the classic 2 over 100 times 300, or just 0.02, convert the percentage. So then here expected would be 6. Let me write a better 6. Let's do one more for 14. I can just go 0.14 times 300, and that would be 42 expected. If I do the same thing for 34, that would expect a number of people of 102. And you see, for convenience, even though we have 6 categories, these numbers do repeat, so I don't really have 6 different calculations here. There's some symmetry for the convenience of a hand calculation, or the distribution it may come from has some symmetry. So I can't just look at these numbers and say, well, 6 isn't the same as 5. What I observed was 15, expected 42. 90 and 102, yeah, it's sort of close. What is close and what is not close? Because I expect, if I just take a sample, even if those people if their categories follow this expected distribution, I'm going to have some fluctuation, some variance is always there. How much is okay and expected, so to speak, and how much variance is going to indicate that, no, maybe these people being observed come from a population that has a different distribution of these categories. I need to have a statistic, a measure that I can rely on and use and defend my conclusion with. So for that, we're going to have 2 columns here. Ultimately, what I want is the comparison distribution, which is the chi-squared distribution, which I'm going to use formula 13.14. I'm going to break it up into 2 steps. You don't have to, but ultimately I want to calculate the square differences between observed and expected square, so that there's no positive negative cancellation, remember, and then I'm going to divide each by the expected, so have a relative square deviation, so to speak, and then I'm going to add those up, and that'll be my chi-squared statistic. So let's just say here the comparison distribution is going to be chi-squared. Fix my D here. And the degrees of freedom will be the categories minus 1. So that'll be a 5. I have to get the, well, actually, let's not calculate anything. And what we usually do is visualize this. We have our chi-squared distribution. Let's put it on the side here. That looks like so. And we're going to have a cutoff that we are okay with. And in this case, they ask for the 1% level. Okay, so 1% of all the possible scores, chi-squared scores, will fall into this section over here, giving us our cutoff, our chi-squared cutoff, which is, well, I go to my data table. I am interested in 5 degrees of freedom, 0.01 alpha, 15.087. 15.087. 15.087. Now I need to see. So anything to the left of this cutoff value will be considered to have normal, natural fluctuations that do happen as I take samples. And anything past that will be considered so extreme that it suggests that these populations do not have the same distribution. Let me just scroll up. So now we have to calculate our observed chi-squared statistic from the information. So that is where we're going to have our observed minus expected. And then you can totally do this in one column. I'm not sure why I'm doing two, but hey, that's what I'm doing. Just to not have a calculation that's too big at once, it might help you to break it up into more steps. So let's do a couple of these. Observed minus expected, that's a -1. -1 squared, let's put it like this, will be a 1. Observed minus expected, that'll be a negative. Well, let's show it in the chat, sure. You don't have to do these in your head. I don't want to give you a false impression that you have to. 15 minus 42, of course, a -27. If we square that, again, you can even go back and put brackets around that and then square it. That's all good. And I get 729. And I can go on like this. I encourage you to calculate these next 4 yourself, and don't just sit back and wait for me to do it. You have to be able to do it yourself to check if you really understand. So we'll take a very quick break, pause if you need more time. Actually, no, before I do that, what I'm going to do is I'm going to finish the whole row, and then you can pause and finish both the squared deviation, so to speak, and the relative, both of these columns for the other 4. So now I'm going to calculate this one over here. Let's just finish the row. Otherwise, we break twice, and that's going to be annoying. So I have 1 divided by expected 1/6. Let's show it there. 1 divided by 6, everyone knows that, 0.1816, repeating. So then I'll round that to 0.17, let's say. And then the next one will be 729 divided by expected, which is 42. And we get 17.36. Okay. So you can do it all just one column. Observed minus expected squared, then divide by expected, and we're only interested in this last column. But if you feel the calculation is too big, break it up into smaller steps to make sure you're correct. We'll take a break here, pause, take as long as you want to fill in all these numbers, and then we'll continue. right, we are back. Hopefully you filled in all of these. I'm going to quickly write them in. We get a 144, 324, 64, and a 196. And then for the column that actually matters, 1.41, 3.18, 1.52, 32.67. All right. So now we add these up. Remember, we have our formula. We add them up. So let's do that in the chat. 0.17 plus 17.36, 1.41, 3.18, 1.52, 32.67. And we get 56.31. This is our chi-squared statistic. 56.31. 56.31. We see that's way out here. Further, I don't really care about the scale. It's in this cutoff region. And we are ready for our conclusion. So we can say here, maybe conclusion. Now we can't write a super pretty conclusion because we don't know the story. So we're just going to have to sort of do a generic one. Since chi-squared observed is greater than chi-squared cutoff, we reject the null hypothesis that this is too extreme. This wouldn't just happen. The evidence suggests that these distributions are actually different. The evidence suggests that I'll just say it like this, the distributions of these populations are different. And our hypothesis testing procedure allowed us to have something more concrete to make this conclusion, and not because we can't just feel, oh yeah, these numbers are not the same. How different is different enough? Because some fluctuation will occur naturally. Where is that line? That is the whole point of having this procedure. All right. So that is one problem we've worked through for the chi-squared goodness of fit. Right. Let me just check my recording here. Everything is good. Okay. Next up, we're going to look at the chi-squared test for independence. And that the one we're going to look at is going to be number 20. So let's go to number 20. Scroll, scroll, scroll. 20 is over here. It has a little bit more of a story, so let's read it first. A comparative psychologist tests rats, chimpanzees, and humans on a particular learning task. The following table shows the numbers of each species that were and were not able to learn the task. Is there a relation between species and ability to learn the task? Use the 1% level. So we want to again go through our hypothesis testing procedure to sketch distribution. And as we go, we'll explain what we're doing. We're not going to write out part C. That's the way we usually do it. But of course, you can take notes of what we're saying, and then you have answered C. So we want to, let's just check there's no follow-up. No, okay. We want to see here or investigate. Is the ability to learn this task independent of the species type? Or is there some connection between these? Well, first step is to copy this table. So I'll say here yes and no for the learning of the task variable. And then we'll have the rat over here, chimp over here, and human over here. So what we observed was for the rat 2 and 28, 8. For the chimp was 4 and 16. For the human, 14 and 6. And you could look at this like, oh yeah, clearly these are different, right? But it's very hard to just guess like that correctly every time. So let's add up these rows and columns. Now, if I can write properly. Add up the rats, we get 30. Now, of course, these numbers come from our table, just like that. Add up the chimps, and 20 were in the study. Add up the humans, 20 were in the study. Add up the rows, rather. 2, that's 6, that's 20. 28 and 16, 44, so 50. We add those up, we get 70. So there were 70 individuals tested in this study. So now I look at the row, the yes row and the no row. Overall, if I merge all of these, there were 20 out of the 70 that were yes, they were able to learn the task, and 50 out of the 70 said no, they were not able to learn the task. So those are the percentages that I'm looking for. So let's say here in total, the yes was 20 out of 70. We change that to a percentage. We get, well, I'll do it in the chat, sure. If you don't know your sevenths, that might need a calculation. And we get 28.57%. And for the no's, we of course get the rest, 50 out of 70. We can do that, sure, no problem. See it in your calculator. Shortcuts don't need to be taken. We calculate it. Now I know Discord gives me a weird fraction, perhaps as an answer. Looking for the decimal, 71.43. And of course, these have to add up to 100 because I only had two outcomes for that learned task variable. So these are what I expect. These are going to give me my expected frequencies. Let's say frequencies, sure. So if there is, let's suppose, if the ability to learn the task is completely independent from the species type, then each of these, rat, chimp, human, should behave according to these percentages. That roughly, it's not going to be precise, roughly almost 30% should be able to learn the task, and almost 70% should not be able to learn the task. If there is a significant deviation from these expected percentages or frequencies, then some species are behaving differently from others, and the ability to learn the task somehow depends on the species type. That's what we're investigating. So let's set up a null hypothesis and a research hypothesis. Of course, we're looking at the populations, rats, chimps, humans. You can write that down as well, but not crucial to do so. So our null hypothesis is that the ability to learn the task is independent from, let's say here, species type. And the research hypothesis that I kind of am hoping to get is that it's not independent. Independent. All right, so under the null hypothesis, the observed frequencies should be pretty close to what I expect. But what does close mean, right? I need a way to measure it. So again, my comparison distribution is going to be a chi-square distribution. And in this case, the degrees of freedom is going to be the number of columns minus 1 and the number of rows minus 1. Or backwards. For number of rows minus 1, number of columns minus 1. So that's 1 times 2, so 2. All right. So we can do one more line here at the alpha level that we're interested in of 0.01. We could visualize this like we did before. Chi-square distribution looks like this. We're going to have our cutoff somewhere so that this region on the right is 1%, just like before. We have a different degrees of freedom here, so let's have a look. What is that cutoff? Not formulas, cutoff. 1%, alpha of 2, 9.211. So that's going to be 9.211. 9.211. Now we want to see, okay, we have a clear cutoff that everyone agrees on. This is a way to defend our conclusions. If from the table of observed scores, observed information, we get a chi-squared that falls to the left of this, that is going to be interpreted as just common natural fluctuation when I take a sample. But if it is further to the right, we consider that to be so extreme and so rare that we wouldn't just stumble upon a chi-squared score like that. And it suggests that, in fact, somewhere there is significant difference in a species from what we would expect if they were truly independent. If species was independent from the ability to learn the tasks. So we have to see, well, okay, according to these frequencies, what do we expect for the number of rats under the null hypothesis that it doesn't matter which species you're in, it's going to be these percentages or very close. What do I expect? Well, I expect 28.57% of the 30 to be in the yes row. So let's calculate that. 28.57%, so over 100, times 30, and I get 8.57 rounded. So I would expect roughly 8 to 9 rats to fall in the yes column if I have a sample of 30. Now 2 doesn't mean anything necessarily. I don't expect it to be exactly 8 or 9. In the no row, I expect 71.43% of 30. Now, of course, that's the rest. Now, I don't round this. I just round to the nearest integer. I just round it when I speak. casually, right? Because then I think of whole rats, of course. We can't have half of the rats learning the skill and the other half of that same rat not learning the skill. That's ridiculous. But in the calculation, I do keep the decimals. So there is some fluctuation between what I expect and what I observed, but that could just be natural fluctuation because of the sampling, right? From one sample to the next, it's going to happen. Let's finish it for the chimp and the human. Now, exactly the same thing. I expect 28.57% of the 20 chimps. Let's do that. 28.57% of the 20 chimps is 5.71. And you see, that's pretty close to what I expected. And then the other one, I'm going to leave to you as 14.29. Now, the nice thing doing this by hand is that the chimp total and the human total are the same. So therefore, the percentages of these totals will also be the same. Only because the totals are the same, and that saves me a little bit of effort. That's nice. Okay, so what have we done here? We can now compare the observed scores, and we have 6 of them, to the expected scores under the null hypothesis if the learned task, ability, and the species column doesn't actually affect each other or are connected in some way, then this is what I would expect. So now our chi-squared statistic again comes from this formula, 13.1. I just have 6 of them. So I'm going to take the observed. This is the no, that's not the observed. This is the observed. This is the expected. I'm going to take the difference, square it, and divide by the expected. So this table is going to get a little crowded. I'm going to make a new table down here, just so it's not too messy. Just copy the row and table headings. Human. Okay, so let's calculate this one. Let's show that one in detail. So it's observed minus expected squared over expected. So the observed was 2 minus expected is 8.57. I'm going to square that, and I'm going to divide that by the expected. Oopsie. 8.57, that came from the percentage calculation. So let's calculate that. We'll do a couple and then we'll pause because there's a lot to do and it's the same thing. We'll pause to give you a chance to see if you could do it. So 2 minus 8.57 in brackets, square that, divide by 8.57, and we get 5.04. All right, so that is how we're going to do it. We're going to compare these observed and expected, 6 pairs like that. For each one, we're going to do this calculation, and we're going to fill in each of these 6 spaces. All right, so I'm going to pause here, take as much time as you need, and see if you can fill in all other 5 numbers. And then we'll be right back. And we're back. Again, take as much time as you need. The numbers I got for the other rat in the rat column is 2.01. For the chimps, it's 0.51 and 0.20. For the humans, 12.04, and 4.81. All right, so now we're going to add up all of these for all of them, the whole thing. That's what this formula says. Add them all up, and that's your chi-squared statistic. So chi-squared observed, when I add them all up, I get 24.61. That is going to be what we write over here. Chi-squared observed, 24.61. So the same calculation happens over and over and over. Yes, when I do it by hand, it's tedious, but it's not that complicated. 24.61. And I see that sits way further than my cutoff, and I'm ready to make my conclusion. So we can say, since, shall I move this up a little bit? Like so. Actually, like so. Since my chi-squared observed was greater, what's wrong with this 2? There we go. Was greater than the chi-squared cutoff, we reject the null hypothesis, of course, in favor of the research hypothesis. Let's make a line here. The evidence suggests that, now there's a lot of ways you could say this, that you could just say in general that the two variables are, are not independent of each other, or we can use words that are more closely connected to the actual question. It's totally your choice. That, let's say here, the ability, you can always go back to the question, right? If you're like, what were the words I should use? Well, let's look at the words they use in the question. Is there a relation between species and ability to learn the task? Is there some connection? Are they independent of each other? No, it doesn't seem like they're independent of each other. The species seem to matter. And you can sort of see it here as well. I don't know which. You see that there's very small contributions by the chimps, meaning they fit the expected breakdown very closely. And the human numbers specifically are the big contributions, ratchet a little bit, to this larger chi-squared score or statistic, which corresponds to the fact that the human scores deviate quite a lot from the expected scores. But how much is enough, right? That's the whole point of the hypothesis test. So the evidence suggests that the ability to learn the task, let's say here, depends on the species, let's say type. You can say a lot of things here. You can phrase this in a lot of ways, right? There's some relationship between them. We don't know what that is, but the evidence suggests that being a rat versus being a chimp versus being a human, that does affect your ability to learn the task somehow. All right. So don't look at this sentence that I wrote and think, oh, I must write my sentence like that. There's a lot of words you can use. You can phrase it as dependence, independence. You can use their words closely using this word relation between species and ability. Lots of ways to phrase it. I'm not going to write down all of them. But hopefully with this problem and its working in detail, you're able to better understand the idea. What is the chi-square test trying to do? what's the logic, what's the reasoning behind this? Because if we understand what we're trying to do, then it's easier to remember the process as well. And it just makes more sense, and it just feels easier when you understand what you're doing instead of just blindly memorizing steps. That's never ideal. All right. Hopefully that was helpful. Like always, let me know if you have any questions, and we will talk again in the next video. Until then.